In this video, we're going to try and understand why it is that when you try and sum up this series, when you try and add up all these terms, it will just get bigger and bigger and bigger. We're going to try and understand why the series diverge. If you look at 1 over n squared from 1 to infinity, this series, when you sum up everything, it will converge. This thing here will diverge. We're going to try and understand why it diverges. Okay, so the first step is to somehow find a way of generating all these terms. So find a way of generating all these terms. So we are going to use the graph y equals 1 over x. So by using the graph 1 over x, we can generate these terms. So when it's 1, this thing here is 1. When it's 2, it's going to be a half. It's going to be a half. When it's 3, it's going to be a third. But then we're going to use Riemann's sum, Riemann's upper sum. So we're going to deliberately create delta x. We're going to deliberately create this width to be 1, and then we're going to create this width here to be 1. So this area here, would be the height, which will be 1, times the width, which will be 1. So this area here will then give us this thing here, and then the next one, well, the height is a half, and then the width is 1. So a half times the width, which is 1. So this thing, so the area here will represent this half here, and then the third, well, the area here would, well, we're going to use Riemann's upper sum to generate all these terms. So the trick here is to create Riemann's sum in such a way that the width, we're going to deliberately create the width delta x to be 1. So now this area here will represent this term, and then this area here, because the height here is, well, when you put 2 into 1 over x, the height will be a half, but then the width is 1. So a half times 1, well, this area here would represent this, a third here. So this area here would represent a third, and then we're going to do it all the way up to n, and then later on we can take the limits as n tends to infinity to sum up from the first term all the way to infinity. But for the time being, let's just take it up to n, to an arbitrary point n. Later on we can take the limit as n tends to infinity. But for the time being, let's just take it up to n. So by using Riemann's upper sum, we can generate all these terms. So if you look at this here, looking at Riemann's sum, so looking at Riemann's sum, so the first one would be this one. This area here would represent this. 1 over 3. This area here would represent 1 over 3, and then it's going to be dot 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 dot, and then for this area here, it will be n minus 1. So this is n minus 1. So you've got to get n minus 1, put it into n minus 1, put it into here. So the height here will be 1 over n minus 1. The point is that the very last rectangle will be n minus 1, because it won't be n. N would be this rectangle here, but we don't care about this rectangle here. We only care about from here up to n. So the very last term will be 1 over n minus 1. It won't be this n here. It won't be this one here. So we don't want, the very last term will be this one here, 1 over n minus 1. So if you look at the integral from the actual integral of 1 over x, so 1 over x is actually the red line, the area underneath the red line. Well, the area underneath the red line will be less than Riemann's sum. So you have to accept that the area underneath the red line here will be less than Riemann's sum, will be less than all the rectangles. Now, going back to our notation for Sn here would represent this is a partial sum of the series. So it's from the first term all the way up to n. So but then if you look at our scenario here, this only takes us from here up to n minus 1. So currently we are here at the moment. we know that the area underneath the red line is going to be less than all the rectangles. But then if you look at our notation, this is something totally different now. But then, well, the point I'm trying to make here is that this is exactly the same as this. So I can say that Sn will be greater than this thing here, because if you look at Sn has an extra bit here. This you have to accept that Sn here is bigger than this thing here, because look, Sn contains an extra tiny bit. So we can actually say Sn here is bigger than this thing here, because if you look at it, Sn is this thing plus this thing here. So Sn, remember, this is just a notation for summing up everything for the first term all the way to n. Well, the point here is that Sn will be bigger than this thing here. And then this thing here is bigger than this thing here. So I can actually say this thing here is less than Sn. So we can actually say this thing here is less than Sn. And then now, if we integrate this, so we've done this before. Integrate this, it will be natural log from 1 to n, and then put this into here, That will then give us this, and then well, natural log of 1. If you look at the natural log graph, natural log of 1 is 0. So this thing here is 0. So it just gives us this. Now take the limit as n tends to infinity. So currently this is Sn up. You're summing up all the terms up to a certain arbitrary n here. So now when you're here, take the limit as n approaches infinity. So when you take the limit as n approaches infinity, this Sn becomes S. Remember, S is you summing up everything from the first term all the way to infinity. Sn is you summing up from the first term all the way up to an arbitrary term n. But then when you take the limit as n capital N tends to infinity, then Sn becomes S. So the point here is that the whole sum here, well, as n tends to infinity, you can see this is just going to get larger and larger and larger. Well, S being always bigger than this thing here. If this thing here is always getting larger and larger and larger, this being always bigger than this must also be getting larger and larger and larger. So you know the whole series will diverge. Okay.